Okay, welcome my friends. In this video, we're going to look at page 3 of the chapter 2 notes for AP Stats. Currently, let me just get my highlighter there. Currently, I'm on the reading guide just because I want to introduce the topics in the video. In today's video, we're going to talk about z-score and transformations of data. Just to introduce those ideas very quickly here. Z-score is one of the most common formulas that we use in this course to describe the location of a particular data point in a distribution. And you should be aware of intuitively what it means, and then also mathematically what is the formula. So here is the formula. A z-score, z, is equal to the difference between a specific observation and the mean of the distribution, all divided by the standard deviation for the distribution. You'll notice I'm using the symbol for population standard deviation because this is in many cases a theoretical analysis where we don't have a specific sample we're talking about, just in general for a whole population. In symbol form, we often write it as z equals x minus mu over sigma. This symbol mu is the symbol for a population mean. I don't recall if we've seen that yet this year, but you'll be seeing quite a bit of it. So you need to know this formula. Now, intuitively, what does it actually tell you? A z-score is measuring location by telling you how many standard deviations from the mean a specific number falls. So what's happening here is we're using the standard deviation as a unit of measure. If a point's really high above an average, it might be a full standard deviation above, or perhaps even 2 or 3 deviations above. If a value is equal to the mean, it is 0 deviations from itself. So its z-score would be 0. And any quantitative value that's lower than the mean is going to have a negative z-score, because when we perform this subtraction, you'll end up with a negative value. Okay. That's the first major topic for today. The other topic that's going to show up on page 3 is transformations. There are lots of instances where you might transform a data set, and by that, I mean you're taking every number in the distribution and applying a certain mathematical operation to it. Perhaps every value gets multiplied by a certain constant or divided by some value. For example, if you are trying to convert a raw test score into a percentage, maybe you're multiplying or dividing. Okay. And when we multiply or divide, we have to be aware that whatever number we multiplied by will also be applied to any measures of center and location. If I double all the values in the data set, the mean is now twice as big. The median is now twice as big. Okay. Measures of spread also get affected by multipliers. Okay. Just have to be careful. There's an absolute value effect here. For example, if we multiplied all our data by a negative number, that doesn't mean we should multiply a standard deviation by a negative, because standard deviation can only be positive. But other than that, the multiplier does apply to any measure of spread, be it standard deviation or range or IQR or things of that nature. The one major aspect of a distribution that does not get affected by these multipliers is the shape. If your distribution was skewed right to begin with, and I multiply every value by 10, those values are more spread out, but the overall shape is the same. The other type of transformation that we often see is adding or subtracting a constant. Be careful here, because adding and subtracting a constant to all our data will continue to affect measures of center and location. If I add 5 points to everyone's test score from last week, don't get excited, I'm not doing that, but if I did, the mean would go up by 5. The Q3 would go up by 5. The minimum would go up by 5. However, adding or subtracting constants does not affect the shape, nor does it affect the spread. If everyone's score gets 5 points added to it, the distance of those individual data points from the mean is still the same. Everything has just been shifted up on a number line. And of course, the shape has not changed either. Okay, so we're going to look at a couple examples on page 3 that help with practicing these ideas. I'm going to scroll down all the way to page 3. And we'll start with example 213. Bundesliga, I hope I'm saying that right, is a professional football league in Germany. La Liga is a league in Spain. Premier League is in England. These are football leagues, right? In each league, the champion is determined by a number of points earned during competitive play. The champs from 2018-2019 season and their points are shown below. We see a couple other things as well. Okay, but which of these teams actually had the most impressive season? We can't necessarily just look at the number of points because, whoops, we don't know for sure. Is the point system the same in all these leagues? I see Manchester City has the highest number of points, but, you know, were there a bunch of teams all right there just below Manchester City? Or is that 98 actually much, much higher than all the other competitors in that league? So we can't just look at these raw numbers because these values are from different distributions. The distribution of the German teams is very much different than the distribution of the Spanish teams and the English teams. Okay, so how do we compare these values from different distributions? One of the things we can do is use the z-score formula that we saw earlier, because z-score can tell us how many standard deviations above the mean these values happen to sit. So while 98 seems to be the highest, is it perhaps possible that one of these other teams was actually more deviations above the mean and hence therefore actually better compared to the competitors in its respective league? That's what we're going to calculate here. And of course, to do those calculations, we would need to know the mean from each of these distributions. We would also need to know the standard deviations. Just keep in mind that these numbers in these right two columns are not specifically measures of the 3 champions. These numbers here are measures of all the teams in each of the respective leagues. Okay, this 17 is not the standard deviation for Bayern Munich. It's the standard deviation for the entire Bundesliga. So feel free to pause the video and try to work out some of these z-scores on your own if you're interested in trying and checking some answers. Okay. And I'm going to start revealing some of these calculations for you to check your work. Z-score, I put a little subscript. Z-score for Bayern Munich specifically, right? The z-scores do describe single teams. But to find the z-score for the Munich team, I'm taking their actual value, subtract from their mean. We're calculating how far above the mean they are. We divide by the standard deviation, resulting in 1.829, interpreted as their score was 1.8 standard deviations above the mean score, which is pretty good. But then we move on to Barcelona. And now we see something that's actually much more impressive. Okay. The mean was higher in the Spanish league, but the standard deviation was much smaller. So on average, teams weren't as far from the mean. So Barcelona, with this really, really high score of 87, is actually over 2.5 deviations above the mean. That's considered more impressive than Bayern Munich from the German league. And of course, we finish it off by checking Manchester City. They had the highest score, but standard deviation was highest in the Premier League. So teams tended to be a little bit more extreme. Manchester City's way up there, but maybe there are other teams with similarly high numbers of points. Therefore, it's not quite as impressive of a result as the Barcelona team. Still pretty good, but just not quite as good. So to conclude here, in an exercise like this, we would say Barcelona was the most impressive team because it was the most standard deviations above their league's mean for points earned. All right, part B. Which league's teams, plural, do you think were the most evenly matched from top to bottom, and why? And we want to make a statistical argument. This question is about all the teams in each league, not just the champions. So that's a clue that we're maybe looking more at stuff over here off to the right. Okay, if you want to pause, think about it, get an answer in your head, feel free to do that. But the answer lies in the standard deviations. If a league's teams are evenly matched, then the teams in that league will tend to earn numbers of points that are similar to each other. Team A might beat Team B, B might beat C, C might beat A. There's going to be a lot more win trading off where not any one particular team is going to be super, super high or super low, which means there would not be as much spread, not as much standard deviation. So evenly matched, I'm probably looking for the team, or excuse me, I'm looking for the league with the smallest standard deviation. For that reason, I'm looking at this 13.9 La Liga. Because it has the smallest standard deviation, its teams are most likely the most evenly matched. On the other side of that, the Premier League with the large standard deviation, those teams are not as evenly matched. There's a lot more spread, a lot more extremes. The good teams are really good. The bad teams are really bad, farther from the mean, not so evenly matched. Well, that's about it. For example, 2.1.3, where we see the use of z-scores for the first time. Looking ahead to 2.1.4 would be next for us. And here we are going to practice some of these transformations that we mentioned earlier. I want you to imagine a class, a relatively small class, only 10 students. They take a 50-point quiz. The results are displayed in both a table and also a dot plot. We want to fill in the rest of the table. There's a bit more to do in the first row. Those are things we can figure out based on what's already there. Then we also want to play out the scenarios of two different transformations. 50-point quiz, maybe a teacher wants to multiply every score by 2 for the sake of turning those scores into percentages. So if X represents the raw score, we could say 2 times X represents percentages. Okay. The other one is adding 3. Maybe there's a grading error. The teacher decides to just give a 3-point boost to everybody across the board. If X was the original scores, this boost would be X plus 3. So think about the rules we talked about with the various transformations from the reading guide, and then look at the headings of each column and think about which of these statistics are measures of center and location, which ones might be measures of spread, which ones might be none of the above. Okay. N in this course is typically just telling you the number of data points. That's not really a measure of anything, or at least not center or spread. X bar, sample mean, is a measure of center. It's telling you the location of the mean, right? SX is standard deviation. This one's a measure of spread. All the numbers of the 5-number summary are measures of location. Some very important locations of interest for us. But IQR and range are measures of spread. And that's going to help us determine how things or which things are going to get changed. Again, pause the video if you like, if you want to try and work out the table on your own. You should do that now. For the first row, I'll do the reveal here. Of course, the IQR is your Q3 minus your Q1 is 4. Range is 18. Shape, well, we have a dot plot to look off, but we could also measure the differences from median to minimum and median to max. Either which way you look at it, we should say that there's a left skew going on here. But now we want to double all the scores. Doubling affects measures of center and location and also spread. So for the most part, we see every single value here getting doubled. The exceptions being N is still 10. There's still 10 scores. There aren't suddenly 20 students involved. But the mean's been doubled. Standard deviation. Everything else has been doubled. Shape remains unchanged. Still going to be a similar left skew. X plus 3, supposing instead of doubling scores, we were just adding 3, okay? This is going to go off the original data again, so I guess we're undoing the doubling. But any measure of center, we're adding 3 to it. 5-number summary, we're adding 3 to it. Standard deviation, still the same. IQR, still the same. Range, still the same. And of course, shape, still the same. Okay, part B. Describe the distribution of z-scores that correspond to the original data above. This is kind of a tricky question. It's going to show us a relationship between the transformations and what z-score formula is doing. So if you think about your z-score formula, I've got it rewritten off to the left. Imagine that you applied this to every single one of the 10 test scores. For every score, we don't necessarily see the exact scores other than off the dot plot, but if you take each one of those numbers, subtract the mean, divide by the standard deviation, you're going to get a new list of numbers. Okay, all these z-scores. What I want you to think about it in terms of is, when we apply that formula, we're actually combining two different flavors of transformation. First, you're doing a shift by subtraction. So that first part of the calculation is going to affect any measures of center or location. It's not going to affect spread. But then you divide, which actually affects everything. It's a combination of two transformations. And so we want to think about, what would that look like in relation to the original data? And I'm going to say a few things. I'm going to cover the big three of shape, center, and spread. And of course, for either form of transformation, shape is not affected. So this distribution of z-scores would still be skewed to the left. For measure of center, I'm going to talk about the new mean. Look up at the table above. The original mean was 42.8. What's the mean of the z-scores? Well, to figure this out, you could, again, take your z-score formula and just plug the mean into it as if it was a typical data point. And of course, now you've got mu minus mu, mean minus itself, which turns into 0. Doesn't matter what you divide by at that point. You get a mean of 0. And that's actually a common theme that shows up throughout this course. When you look at a list of z-scores, the center is always the number 0. 0 units from the mean, which makes sense because the whole premise of z-score is treating the standard deviation as a unit of measurement. The center is 0 units from itself. For spread, okay, the original standard deviation was 5.5, but now we're switching to a system where we're going to use that standard deviation as the unit of measurement. So instead of talking about scores being 5.5 away, now we'd say they're 1 unit away, 1 standard deviation away. I guess one way to think about it is to imagine a data point that was literally one standard deviation away from the mean. Okay. I guess you could figure that data point out by taking 42.8 and adding 5.5. But if you were to do that and then subtract the mean, you're going to end up with 5.5 divided by 5.5. Point being, the result is 1. This is a number that shows up throughout the year when we look at distributions of z-scores. It doesn't matter what the standard deviation was originally. Now it becomes 1 because it's one copy of itself. I would not worry too much if that seemed a little fuzzy here. It's going to be more important later in the course when we've talked about it a bit more. So I don't want you to lose any sleep over that example. It's kind of some foreshadowing. I think we're ready to move on to the final example, which in a way is a little bit more foreshadowing, although we will see some of this in 2.2. A density curve, as you know from your reading, is a theoretical model of a distribution. It tends to be presented with smooth curves. It doesn't take into account the irregularities that you tend to see in real world data. It doesn't include outliers. It just shows you generally how we expect things to work out in a perfect theoretical model. We're going to start using them next section when we talk about bell curves to describe a normal distribution. A bell curve is a density curve. But before we get into that, it's good to understand what qualifies as a density curve. There are two main properties I want you to be aware of, and these are the answers for part A. Why is this a legitimate density curve? Because firstly, it's located on or above the horizontal axis. It never goes below. And the area, if you were somehow able to calculate this green area, would be exactly 1. I don't want to say too much else about calculating that area because not everyone in the course has necessarily taken calculus, but if you have taken calculus, perhaps you know that something like this could be calculated maybe with an integral if you had some kind of equation to describe the density curve. But we don't have to know how to do that for this course. What is important is if we're given certain areas, we understand that the areas of these subregions, like this dark green, are really telling you what percent of your data, what percent of the distribution lies between the bounding numbers on the horizontal axis. So whatever this graph is measuring here, I don't know what it is, some list of numbers ranging from, looks like about 0 up to 20 or something. What percent of those numbers were between 7 and 8? Well, this shaded green area is marked as 0.12, so that means about 12% of the numbers in that distribution are between 7 and 8. For part C, marking the location of the median, I don't really like this question. It's hard to do very exactly, so your best bet is to put the median probably pretty near wherever the peak is. Okay. And then for the mean, all I'm really getting at here is, well, this shape is not perfectly symmetrical. It's got a skew to the left. So we would expect the mean to be a little bit lower than the median. Mean is less than the median because of the non-resistance of the mean and due to the fact that the distribution is skewed left. And it looks like that concludes this video. If you have any questions, feel free to email or ask me when I get back to class. Thanks for watching.